Now, in chapter 32, we're going to apply the concepts of direct likelihood to the case of the age-related macular degeneration trial, where the outcome is, remember, visual acuity, the number of letters we can correctly read on a vision chart, and we are, of course, going to allow for a treatment effect, but that treatment effect we further allow to be specific for each of the measurement occasions. So TI is the treatment that patient number I takes, 0 for placebo, 1 for interferon alpha, the active treatment. But you see that on the parameters beta 1 and beta 2, there is a J indicating that you have intercepts, not so important, but you also have 4 treatment effects at each one of the 4 follow-up occasions, 4, 12, 24, and 52 weeks. Okay, what we're going to do is we're going to look at a marginal mean model with generalized estimating equations, and we're going to look at a model using the generalized linear mixed model, indeed, in this case. So, let's do a complete case analysis to begin with. Let's do a complete case analysis on the continuous outcome, that means, and let's do one on the discrete outcome, because remember, we have the number of letters we can read and that we consider continued, but we also have the number, whether or not we have increased vision. And then we do the same for LOCF, yes or no. Okay. In the continuous case, of course, we're going to use a linear mixed model, as we have said a few pages ago. So that's the model for the continuous outcome. Subsequently, we will look at GE and the generalized linear mixed model for a non-continuous outcome. Now, you must remember at this stage that both the linear mixed model as well as the generalized linear mixed model are likelihood-based methods. So everything I gave in terms of theory so far for missing data, the likelihood theory holds for likelihood-based approaches. So if I have a fully specified model and likelihood, I can go ahead. In other words, I didn't restrict myself to continuous data, but that said, GEE is out of the likelihood framework. For that, I need weighted estimating equations, for example. Okay, so that's the program for the linear mixed model, which you can look at in a bit more detail if you want, but it's a standard approach of that model. I can also do generalized estimating equations, and for that matter, it's also a standard approach, which for now, at this stage, without really going into the details of weighted estimating equations yet, I can do with the more classical ProgGenMod and the more recent ProgGEE. Now, you can look at these two programs for a long time. The only difference is the ProgGenMod versus ProgGEE statement. Other than that, they're entirely equivalent. I have my bin-diff here. I have the time and treatment by time variable. They're both class variables. So in other words, the treatment by time will produce the 4 treatment effects. The same was true in the linear mixed model case. Good. And then to top it off, for the generalized linear mixed model, I can use NL-mixed. I can also use ProgGlim-mixed, for example, where it's the same kind of approach, except that I now also have included a random intercept. For the nonlinear mixed model, I shouldn't say that. I should actually say for the generalized linear mixed model fitted with ProgNL-mixed, I can use this particular code where, remember, with NL-mixed, there's a bit more flexibility, but there is also more programming to do. You spell out entirely your model here, where beta 1,1, beta 1,2, beta 1,3, beta 4,4 are the intercepts, and then beta 2,1, beta 2,2, beta 2,3, and beta 2,4 are the slopes that only apply, the slopes, not really the slopes, they are the treatment effects, because they apply only when the treatment is equal to the active treatment rather than the placebo treatment. Okay, so here's an overview. We have for the linear mixed model the CC analysis, last observation carried forward, and then the MAR valid direct likelihood method. Now, we can look at the parameters and we see that some go up, some go down. CC parameters seem to have a somewhat larger standard there than some of the LOCF parameters, but it's not always the case. So what happens to the p-values? Well, let's look at the most important one, treatment effect at the end. Guess what again? Direct likelihood produces here on the continuous outcome a significant treatment effect which is missed with the other two methods indeed. It's different at different times. So you may say, hey, it still tells us that, well, if LOC, it's still consistent with the myth, which is generally not true, but anyway, we don't have any evidence against it here. CC and LOCF produce larger p-values, so if you put yourself in the position of protecting the public, you may say, well, it's better that we don't find a treatment effect that's not there. It's better this way, where something that is perhaps there but marginally is not found. Okay, well, one thing that you have to know is that this effect here points to harm. The treatment effect, if you look at a sign and study it in this way, will tell you that people's visual acuity is better under placebo than the active treatment. And the reason is because this treatment is administered by direct injection into the eye. The highest dose is very viscose, so that's syrupy, which means it essentially blocks vision. The treatment doesn't work so well, it blocks vision, so people see less well with the active treatment than with placebo. So you better find that, don't you think? Good. Then we have, for the GE analysis, the PQL version, but we know in the meantime that PQL is not something to really strongly advocate, and we have the numerical integration version here. Again, CC, LOCF, direct likelihood. This, by the way, is the generalized linear mixed model. Question is, where is generalized estimating equations? It's a very good question indeed, but generalized estimating equations need weighted generalized estimating equation, and that we haven't done so far. So that will be the topic of the next chapter, of course.